Okay. Good morning. Okay. Good morning, everyone. So it's about time to have today's seminar, and then today we have 4 presenters. Then for each presenters, we may open for 2 questions only. Okay. And then I think you may start with you.
Good morning, everyone. I'm presenter Shannon today. The topic I'm going to introduce is design and implementation of parent-child less model predictive control for optimal power display in electrical charging station. And my advisor is Professor Shen Yixin. Here is today's outline. First, I'll go over the abstract and introduction. Then explain the system architecture. Next, I'll describe our power display system, including the simulation process and control strategy. Finally, I'll talk about total energy density, show the simulation results with the application. We propose an optimal power display system, or PDS, for electrical charging stations using parent-child and model predictive control. The key feature of our work is the total energy density strategy. We build this into the PC to make sure every bus is charged enough before it's executed. Our proposed system optimizes power dispatch based on several real-time factors. Charging demands, the actual and target state of charge, bus schedules, grid dynamics, and total energy density. When compared to conventional average distribution strategy, our PC has PDS reduces both electricity costs and the total energy density. As electric buses become more common, we need efficient charging to keep the system stable. However, dynamic charging during the day isn't practical. Traditional methods that reduce power fully open can keep power dynamic. That's why we developed the PDS using PCMPC is optimization power storage in real time. By improving total energy density, we make sure buses are ready on time, keeping the service reliable. This is our hardware setup. As you can see, power flow represented by solid line comes from the grid and renewable energy to power the station and buses. Our controller, the PCS, manages everything with the command flow shown on the dash line. This flow chart shows our simulation. Part A is data implementation. We set a request that the power with vehicles and their data and simulate events. Part B is the configuration process. The next loop, the system calculates available power and target SOC. It switches buses to charge and distribute power. We also include a visual limit for elements. On the left is a simple view of our data report. The table shows the total power plus enter. The horizontal axis is the bus number and the vertical axis is the time. Each cell shows if a bus is on route, charging, or out of range. To make the simulation more real, we added bus delay using a normal distribution. We use different settings for EV and price times. For example, during peak hours of the night, the average delay is 5 minutes, while rate of peak hours of red time is only 2 minutes. Now for parameters. The most important one is available power. It's calculated by taking the horizontal power plus total energy and subtracting the station's load. You can see in the graph that renewable energy is much higher in summer than in winter. Temperature also affects energy use because of air conditioning. We use a mathematical function as copied to our list. As the graph shows, buses are most efficient at 22 degrees Celsius, and they use more energy in very hot or cold weather. Energy use directly changes the target SOC. We use this formula to find how much energy is needed for the next trip. It considers the trip, distance, energy consumption, and the approximately percent of target energy. Let's look at the controller. First, standard and basic. Our goal is to find the best power setting PI to minimize this function. Let's go while looking at the gate between the target SOC and the actual SOC, while considering how urgent the charging setting. Lower SOC means priority. To solve this, we return the crucial the output state between PV and PX. This keeps the process both optimal and safe for the hardware. Now for the current trial MPC. Standard MPC often ignores the triple Chinese stage which wastes power. Our current MPC uses a more fast power limit to predict this limits early. It also uses the dynamic boost gain to speed up charging faster than active process. This way we can move extra power to proceed as needed possible. The current MPC also ranks urgency and brightness constraints. It gives each bus an urgency score to prioritize the task needs. Also, if a bus is almost full, we reduce its max power limit and use constant cycling to retire power up out to prevent overcharging. The trial MPC handles the final power distribution. Its goal is to match the reference set by the current controller. Like before, we use quarterly programming to solve this efficiently in real time. The solution for CMPC is very similar to standard MPC. The main difference is that we use the tightest limit EUV from the parent. This two-layer structure allows for much more precise charging during the state. To protect the battery's health, we implemented a triple charging limit. As shown in this graph, the maximum charge power is reduced when the bus's SOC is below 50% or above 80%. We implemented this nonlinear limit using a sigmoid function. To evaluate the system's performance, we define a metric. The cumulative calculates the total SOC shortfall. This is the sum of the difference between the current SOC and the actual SOC, cumulative for every bus and after completing every charging round trip. The smaller the PV, the better. This table summarizes our simulation parameters. Firstly, a list of 35 battery properties and 13 charges over a 24-hour period. We compare summer and winter scenarios to evaluate the controller performance under varying levels of renewable energy mobility. Now let's look at the result for the winter scenario. The graphs on the left show the actual SOC as solid line and the target SOC as dashed line. On the right, we have the available power, total power consumption of the chargers, and the cumulative total energy deficit. You can see that the total power consumption always stays below the available power limit. We can also observe two charging peaks green and movement in the middle. Finally, look at the green line, which represents the total energy deficit. It's clear that the DC curve for PCMPC is much lower than the other two methods. The results in summer are very similar to the winter. However, you can notice that the target SOC in summer is slightly higher, and the changes are more significant than in the winter scenario. This is because the energy consumption of electric buses increases at higher temperatures. This table summarizes the overall performance of our system. In the winter scenario, compared to average distribution charging, our proposed PCMPC reduced the total energy deficit by 26.74%, and it reduced the electricity cost by 2.1%. The results in summer are also very positive. Even with large fluctuations, PCMPC achieved a 17.19% reduction in EV and reduced cost by 2.16%. The results prove that PCMPC is more effective and economical than conventional method in both seasons. In conclusion, we built a PCS-used PCMPC that considers schedule, real-time SOC, and temperature. Our system successfully reduced cost and energy deficit compared to standard methods. In the future, we hope to add a battery aging model to help batteries last even longer. This is my reference literature. Thank you for your listening.
Okay, thank you. So I would like to open the floor for questions.
In your research, you mentioned that standard MPC often results in wasted power because it cannot anticipate hardware constraints. How does the parents and PCs demonstrate our limits of this wasted power problem during the trickle tracking stage?
Standard DC lacks the ability to foresee how the charging function. It might allocate high power to a bus over its 18% SLC limit. Only small assets are cut off by the trickle tracking limit, leading to wasted capacity. In contrast, our PCNPC incorporates a sigmoid as power limit directly into the reference population. This allows the controller to predict from the bus the entire trickle function and proactively reallocate that power to other buses that still have high demand, thereby improving the station's overall power utilization.
You use total energy efficient as a key performance metric. Since research typically use average SLC, why was it necessary to design this specific function, and how does the reducing TED improve the operational stability of the bus station?
Total energy deficit represents the total energy that buses struggle to receive compared to their target SOC by the end of charging. While average SOC shows the general status, it can hide individual cases where specific buses are severely undercharged. By minimizing TD, we ensure each bus reaches a satisfactory level for its entry within the designated time. Reducing TD directly translates to better operational results, as it minimizes the risk of a bus running out of power during service.
Okay, thank you. Yeah. Since today we have the 4 presenters, so we only open for 2 questions for each presenters. And then may I invite the next presenter, Fan Gongli.
Hi everyone, I'm Feng Yinghuai. My research title, Diversity, Preserving and Home Mobility Assessment, the future architecture of linear weight radar and thermal image. My advisor is Shi Haohuang. This training is divided into 5 main sections. First, I will introduce the research background and motivation, and point out the core problem and conclusion of the study, and review the nature and the limitation of distinct technologies. The third section will detail the experimental procedure from data collection to the model prediction output. The fourth section covers the experiment design and result analysis. Finally, I will summarize the contribution of this research and countermeasure direction. As the global population age, issues like mobility signal for clients and a higher rate of falling as some major concerns in public health and long-term care all can lead to texture, disability, and low quality of life. They also increase the burden on family and healthcare system. Because of this, the assessment of the person mobility is a very important research direction in elderly health monitoring. In clinical practice, the count and goal is widely used to evaluate mobility balance and progress. During the test, a person stand out on a chair, walk, turn around, walk back, and sit down. The total time is kept to complete this is a key indicator of the mobility. Because this simple fact can clinically inform, the POC test is heavily used for for the elderly, rehabilitation, and people with neurodegenerative disease. However, traditional TUV tests usually rely on manual science and human observation. This approach can be subjective. More importantly, it makes it very difficult to capture detailed information about this specific movement phase, and actually how much time it can spend out walking, turning, or sitting up, and if there are any abnormal variation during this stage. The core question of this study is how can we achieve high precision non-intrusive and quality sustaining TUG monitoring form. To achieve this, we face two main challenges. First one is the elimination of single modality. Data is noisy and thermal image related. A single sensor simply cannot balance the stability and accuracy. Point two is difficult to find point annotation. The TUV test is through continuous process, making it extremely hard to pinpoint apply action mission. Based on this challenge, our research offers three main contributions. First, we validate the power of our multimodal fusion architecture. Second, we achieve stable action segmentation by successfully divide the TUV test into six continuous phases. Third, we significantly improve the model's generalization ability of unseen subject. To further explain why our system is necessary, let's review the existing technology and their limitation. Currently, wearable devices are highly accurate, but they are inconvenient to wear at home, leading to low compliance among the elderly. On the other hand, non-contact RGB camera can introduce, but they raise several privacy concerns. Most people don't want camera in the beginning stage. This limitation leads us directly to our research gap. Most current non-contact studies rely on simple sensor, which is easily affected by noise. More importantly, existing TUG research mostly focuses only on the total completion time, making fine grained segmentation of the spectrum. This is actually why we propose our multimodal fusion system to perfectly fill this gap by solving the issue, the privacy, user convenience, and precise action segmentation all at once. To overcome the limitation of single sensor eye definition, let's look at our proposed system pipeline. We design a complete end-to-end pipeline from data collection to final analysis. By using multimodal fusion, we achieve precise home mobility assessment while fully protecting privacy. The entire architecture consists of 5 main steps. Step 1 is power setup. We set up a unitary radar and the thermal camera to collect synchronized data from the subject, and we carefully label the data to establish the ground truth. Step 2 is data reprocessing. Since raw sensor data, especially from the radar, often contain environmental noise, we clean and filter the signal in the stage. We also perfectly align the timeline of both sensors to ensure we clearly map onto the subject. Step 3 is visual extraction. We proceed the two modalities directly. We extract dynamic and depth feature from the radar, and spatial contour and thermal feature from the thermal image. Step 4 is multimodal fusion. This is the core of our system. We combine these two steps of the future features to visual level fusion. In this step, the dynamic data from the radar and the contour data from thermal camera perfectly complement each other, and frankly boosting the robustness of our feature. Step 5 is prediction. Based on these powerful tools, our model can accurately recognize the 6 continuous actions based on phase of the TUV test and precisely pinpoint every key sign transmission. To this step with successfully built an automated assessment system that is both highly accurate and privacy preserving. And now let's look at the experiment setup and evaluation metrics. You can see in the scenes diagram on the top right, the experimental was conducted in a 35 by 5 meter enclosed space. The chair was placed on the start point. The subject starts on the chair, walks 3 meters forward, turns around and walks back. For each test, we label 7 specific time points at the start and moment of start out straight. This expecting the turning point, return to the chair and fully sitting down. All our recording device, the radar, the thermal camera, and TV camera use 3D or frontier labeling were set out 4 meters directly in front of the chair, facing the subject. Moving on the data, we collect data from 18 subjects. In each person performing self-PUG test, to simulate different mobility level with the time to condition. 5 tests were done at normal pace under 12 seconds, and 2 tests were done to slower pace over 12 seconds. This slower pace helps us mimic the movement pattern of the elderly or patient with mobility issues. To fully evaluate our system performance, we select 3 key metrics: PUG time, test coefficient, and duration data. This slide visualizes the PUG timeline measured by classification. As we can see in the chart, the x-axis represents time in seconds, and the different color represent different action phase. For example, dark blue is stance, and orange is working out. For each test action, we will see for example bar. The top bar is from true. The next 3 bars represent the prediction from fusion model and weather-only model and the thermal-only model representative. The chart includes normal pace test, like section 1 and 3, finished in about 10 seconds, as well as slow test simulate elderly movement, like section 6 and 7, taking over 20 seconds. The most important finding here is the alignment. You can clearly see that the multi-part, the second part in each group, align almost perfect to the function. It currently captures both the transmission point and the total time. And it maintains these high accuracy in both normal and slow scenarios. In contrast, the single sensor model show obvious deviation. The open goal to catch possible precision by turning and sitting down, which lead to shift time point and duration data. To sum up, this virtual result strongly proves that our multi-model fusion approach with efficiency compensate for the lineation of single sensor, achieve high, stable, and precise time-frame action implementation. This picture which shows the effect coefficient for different action phase. The red dashed line is set at 0.8, serving as our baseline for highly accurate implementation. As you can see, the twin bar represent our fusion model, consistent outperform the single sensor model across almost the whole case. What especially notable is that during high charge transition, like stand up and sitting down, the performance of single sensor drops significantly. However, our future model remains highly robust and accurate. This picture below shows the distribution of urine age. The red dashed line at 0 represents a perfect zero error prediction. Positive view in overestimation and negative view in under estimation. the fusion model is even more obvious. The green dots are highly discerned along the middle line with very short ridges. The mean is high L is extremely small and the relative is very low. In stark contrast, the single sensor model shows the fast and long whiskers is actually doing now and down. Both their third time deviation and height is appeared. Sunlight. This combination is called strongly proof that our model fusion not only maximize segmentation accuracy but also significantly reduce high prediction that it truly provide a high stable and reliable DB assessment system. To summarize our core conclusion, first we successfully developed an intrusive monitoring system. By combining radar and thermal image, our system ensures good privacy protect will be fully compatible of 24/7 operation. Second, our experimental data validate the power of model fusion. The result proved that our dual sensor approach directly outperforms single sensor setup. It especially overcome unimodel elimination such as radar noise and thermal blind spot. Third, regarding fine-grained action segmentation, we successfully divided the fusion test into 6 distinct phases by leveraging the complementary strength of both modeling. Our system precisely captures subtle action transition. This high accuracy rate increases the potential view for clinical assessment. To ahead, we have two main directions for future development. The first direction is dataset expansion. Including subjects with different health conditions and mobility level will be crucial. This will further improve the model robustness and generalize cross-deliver calculation. The second direction is optimize our function. In the future, we tend to use RGB video combined with advanced data tracking region to create even more precise function label. This will further enhance the accuracy of our model training and validation. This is my reference. Thank you for listening.
Thank you. So, any questions from the floor? Okay.
In your experiment shows that the sensors are placed 4 meters directly in ground. What if the elderly person walking path is not perfectly straight towards the sensor? How is the system robustness regarding different angles of accuracy?
Okay. Regarding frontal walking angle, our current model is indeed training primarily on frontal data. For future real-world deployment, we may consider using data augmentation with multi-side angle to train the model. Alternatively, we would recommend installing the system in area with more fixed movement tests, such as always, to ensure optimal performance. Any other questions?
Therefore, you mentioned using feature level fusion. Why did you choose feature level fusion? Did you consider the
decision level fusion or data level fusion, and what are the differences?
Okay. When you consider other methods for data level fusion, it is very difficult to directly overlay the data because the dimension and characteristics of radar and thermal image are just too different. As for decision level fusion, it involves the two model making subject, predict, and then voting. This approach looks the opportunity for the two modalities to complement each other at the underlying feature level. We choose feature level fusion because this allows the neural network to automatically weigh the dynamic feature of the radar and the spectral contour feature of the thermal camera across different action days during the learning process. This achieves true complementarity.
Okay, thank you. Thank you for the information. Then we invite the next presenter, Ying Yu.
Good morning, everyone. My name is Ying Yu. Today I will present facial age estimation analysis based on convolutional neural network and transformer architectures. This study was conducted under the supervision of Professor Kang Yiwei. And this is my outline. Introduction. As imagery processing technologies continue to mature, applications related to facial recognition have become widespread in daily life. With age recognition technology emerging as a core area of significant interest, this study aims to introduce advanced deep learning techniques for age estimation through the extraction of facial features. Age estimation can be applied across various domains, such as assessing health conditions in the medical field, as well as in the domestic industry, law enforcement, forensic science, human-computer interaction, and security control. In the realm of deep learning research, the primary focus can be divided into predicting biological age and apparent age. From a model design perspective, approaches are generally categorized into classification problems, which assign a specific age to predefined intervals, and regression problems, which treat age as a continuous numerical value. This study will focus primarily on predicting biological age utilizing a regression-based approach. Related work. A string transformer is the next generation vision backbone introduced following the vision transformer, EIT, primarily designed to overcome EIT's bottleneck where computational complexity scale quadratically with high resolution images. A string transformer uses shift window subrotation to exchange local and global information. We also adopt a senior-like hierarchical structure to extract full-size-scale pictures. This design successfully drops the complexity from projected to linear, making the model highly versatile and efficient. ConvNet is a pure convolutional neural network that systematically modernizes traditional CNN by borrowing key design principles from the Swing transformer. In terms of structural optimizations, it displays the initial Gaussian layer with an overlapping convolution strategy, also known as patchify to better preserve spatial information. We also adjust the stacking ratio of its computational blocks to 3393, aligning with the low distribution of the Swing transformer. Furthermore, ConvNet employs large 7x7 kernels and depthwise convolutions to simulate the global velocity file of transformers. It also incorporates an inverted bottleneck designed to expand hidden layers dimensions and moves the depthwise convolution layer upward, similar to transformers layout. These changes enhance feature extraction while reducing computational complexity. These optimizations allow ConvNet to achieve accuracy and scalability comparable to a legacy transformers model. Phone-fast VIT and mobile-net V4 are high-performance live-layer network designed specifically for resource-constrained edge devices. For fast VIT, it uses a hybrid architecture that creates dynamic convolutions early on and minimizes heavy self-attention. Its chief innovation is using the Red-Miser module and structural reparameterization. This allows it to merge complex range into a single step during inference, which drastically cuts down memory access costs without losing accuracy. On the other hand, mobile-net V4 introduced the universal inverted bottleneck UID and mobile anti-weight attention. It adopts a hardware-aware roofline designed to smartly balance compute-intensive and memory-intensive layers. Ultimately, both models achieve an exceptional balance between hardware load, memory footprint, and endurance throughput, making them highly efficient for practical deployment. Methodology. We utilize 4 types of models: Swing transformer, ConvNet, fast VIT, and mobile-net V4. For Swing transformer and ConvNet, we employ the timing and base scales to aim for optimal accuracy. Fast VIT and mobile-net V4 were primarily used to evaluate and compare their network complexity. Regarding their architecture, we modify the pre-trained platforms by adding a regression layer for continuous edge prediction. We also choose smooth L1 loss to make the model more robust against outliers and noise late in the dataset. For dataset for this study, we use the UTK-based dataset. It contains over 20,000 facial images with precise edge annotations ranging from 0 to 116 years old. To train and evaluate our models, we split the data into 3 sets. 80% was used for training, 10% for validation, and the remaining 10% was reserved for testing. Finally, we apply several pre-processing and augmentation steps to improve model roughness. First, all images were resized to two 24 by 224 pixels. We choose resize over random cropping to make sure no important facial features were lost. Next, we apply spatial augmentations, including random horizontal shifts and rotations within plus or minus splitting degrees to simulate different flip poses. We also apply photometry augmentations by random adjusting brightness and contrast by plus or minus 20%. Lastly, we perform channel-wise normalization using the standard image naming and standard deviation values. Mean absolute error (MAE) is the most widely adopted standard evaluation metric in age prediction tests. It is defined as the average of the absolute difference between the model's predicted age and the actual annotated age. This study will utilize the overall MAE achieved by the models on the test set as a core quantitative basis for measuring the prediction accuracy of each network application. This is the quantitative result of our experience measured by MAE. As you can see from the table, swing space achieved the best result with an MAE of 4.2. Closely behind is complex space with an MAE of 4.21. The gap between them is only 0.01, which is extremely small. This narrow margin shows that both models are not only accurate in standard image classification, but also perform almost equally well in the more challenging text of continuous age estimation. This table presents the evaluation of model complexity and computational efficiency. Here we compare the models across both metric parameters, blocks, peak memory usage, and inference throughput. These results show that although swing space and complex space achieve the lowest MAE, they require significantly more parameters and memory. On the other hand, while MobileNet even sacrifices a bit of accuracy, it truly excels in computational efficiency. We can see a massive advantage in its throughput, as it processes images over 5 times faster than swing space. To evaluate how image quality applies to the estimation result, we group the predictions into 7 age intervals and selected the 2 best and worst tests from each group. In the top 2 rows, we can see the best predictions. These images typically share three key characteristics: clean quality, high image quality, and low facial occlusions. Under these ideal conditions, the models can accurately extract aging features, resulting in minimal errors. The bottom 2 rows displays the worst prediction, highlighting several key factors that cause severely with predictions. We found that poor image quality, such as low resolution or motion blur, distribution aging, microtextures like wrinkles and spots, thermal, makeup, and image filters severely mask the true skin condition. While external occlusion like glasses or pens disprove the structural integrity of the face. Finally, non-frontal poses or extreme camera angles distort facial proportions and introduce uneven shadows. approximately confusing the model's visual alignment. In conclusion, imaging noise and cause variations under non-ideal conditions are the primary reasons behind extreme errors in age estimation. Conclusion: the result of this study demonstrate that convolutional applications remain competitive in complex visual text. Likewise, architecture shows clean advantage in inference efficiency and memory consumption. However, the underrepresentation of Asian demographics in the UT-based dataset may limit the general visibility of our findings. Future research directions include integrating multimodal information, such as body features and facial expressions, to enrich feature representation and applying denoising techniques to enhance readiness under real-world imaging conditions. Thank you.
Thank you. So, any questions? I will open the floor for questions. Okay, if no question, would you please go back to the result? Because if I'm not sorry, if I'm not mistaken, you utilize 4 different models, right? The screen and fast VIP, mobile VIP, mobile V4. All of this is proposed by other research group. So what is your own model? So is it your master study? So your master project, right? So I think in your supervisor may expect you can come out with a new model or new methodology to solve or to solve these specific problems, right? Oh, really? Okay. Okay. So let's welcome the last presenter, Deng Kai-hong.
Good morning, everyone. I'm Kai-hong Deng, and today I'm honored to present my research, Image-based human tracking system, conducted under the supervision battery work. This is the outline of today's presentation. I will start with the research motivation and the map. Then I will introduce the human mass spectrum map and explain how its draw feature and are chart. Next, I will describe the GRU-based identification model and how it was to identify the target user. After that, I will show the test results, including the model performance and the human identification experiment. Finally, I will give a conclusion. In recent years, human following robots have attracted increasing attention in small mobility and human-robot interaction. Many existing systems rely on the device carried by the user, such as smartphone or Bluetooth terminal, to perform localization and tracking. Through those devices based on that are usually
identification feature, the system can recognize and check the target with user without requiring any additional wearable device. This approach improves both system automatic and user convenience. This study focuses on recognizing and tracking a specific person based on the bad posture and the gait pattern. In this system, the recognizing model classifies each person into two categories, mentor and stranger. Top camera capture the view body information and the media titles capture the visual coordinate from a human body. Those joint coordinates are used time series data from a GRU-based model. Once the person is classified as a master, the system identifies the individual as a specific person. Media type is used to extract the human joint coordinate from back view image and recognizing change the back posture. Through media types provide 33 body lemma with X and Y and Z coordinates. Not all joints are strength related to working motion. Therefore, this study slides 12 key joints as an input feature for recognition model. Those joints including the shoulder, elbow, wrist, hip, knee, and the ankle on both sides of the body. Each frame is really used OpenCV convert to RGB and persist to obtain 3D coordinate of 12 joints, forming a 12 times 3 feature beacon. Working cycle is about 1 second or 30 frames, so every 30 frames from one data sample. A sample is named as a master or stranger from a sample. The data set including the 7,431 master sample and 5,938 stranger sample with a rate about 5 to 4. This study uses a gait recurrent unit GRU as a temporal classification model to learn joint coordinate change during walking. The GRU retain past motion information mainly efficient as sequential data. After the training, it can identify a person based on a temporal movement pattern. The recite gate decides wherever to forget past information and update gate control how much old and new information to combine. Allow a model to handle both long-term and short-term dependencies. The GRU model inclusion is 30 by 36. Represent the 30 frames of a 12 joint with 3D coordinates. The first GRU layer has 128 units and return all time state. L2 regular reagent and draw out with a rate about 0.3 are applied to overfitting. The second GRU layer has 74 units and output only the final hiding state, which summarizes overall motion information. After that, the next layer with 32 learn-on and redo activation extra high-level feature. Finally, the sigmoid output layer gives a probability for binary classification. The most point to 1 indicate the master, when the most point to 0 indicate the stranger. After the training, we compare RN, GRU, and SDN in terms of the accuracy, training type, endurance, speed, model size, and the number of the parameters. The RN is slightly and fast, but in recognizing performance is lower. The LCN achieves best accuracy, but it is largest model size and the most parameters. The GRU provides a better balance between performance and efficiency. Therefore, we select the GRU as the final recognition model. The test set including 100 sample, 50 master sample, and 50 stranger sample. Here is the configuration for 3 models. The RN has more classification between master and stranger. We compare with RN, GRU, and SDN, reducing the number of incorrect prediction. The GRU shows reliability result between the This suppose we previously saw that the GRU is suitable for this recognition test. This slide shows the ROC curve of the GRU model. The ABC both of is 0.8AC52, indicate good classification ability. Instead of using a threshold of 0.5, the best threshold was like using a Golden index. The final threshold was 0.5362. This threshold help the balance recognition, performance, and reducing the misclassification. This slide shows the flow of the human identification experience. This slide initialize camera parameter and actively real-time joint detect. When the time working, 30 frames of the joint data are captured and sent to training GRU model. If the test is classified as a master, the system will mark the body contour and recording the position information. The training model detects the human body with average confidence score of 0.8219, crossing 30 frames. When the target classified as a master, the contour and the joint point are marked on the screen. The recording information including dot and angle, such as the dot of 2.09 meter and the angle of 2.6 degrees. This information provides a system which with the target position potential position. This system utilizes the dot camera and as the main input and integrally media hyperpose extra motor feature. Those features are used to training a GRU-based model from a bad posture. The experiment shows the model can identify the target environment based on temporal position feature. Overall, this study demonstrated of potential of using a deep learning based on temporal model for human identity based on the body posture and face data. Thanks for everyone listening.
Thank you. Any questions?
Why did you choose GRU instead of the STM?
STM achieved a slightly better accuracy, but it had a more parameter and larger model size. GRU provides a better balance between accuracy and efficiency. So we select GRU as the final model.
Why were only 12 key joint select instead of using all 33 landmarks?
Not all 33 media pi landmarks are strength related to working model. So we select 12 key joints to reducing unnecessary features and help the model focus on working related joint.
So basically, this research is about recognize the master and stranger, but I don't see the comparison about which one is the master and which one is the stranger. So I just want to clarify that what is the research actually about? Where's the comparison?
Which one?
So what's the real reply? What's the real response? 中文回答。哦，好吧，先他先。你的主题大，对，你的研究主题大就是
由人体的关节姿势背后人体关节姿势去辨识说它是
是讲是 exposure 嘛，他说那你没有辨识说到底那个是 master exposure 所以到底目的是要做什么？
这我的目的主要是用背后的动态去辨识说他这个人是不是主人，他是默认的，然后这边我们只有碰到说他辨识到底我的状态，但我没有碰到说他辨识默认。
对啊，因为在上面没有秀出来。
是我确实没有把默认辨识的10个方就是辨识。
Okay. 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 Thank you. Yeah. Okay. So thank you for your attention. Then I think I would like to close the session and thank you.